Hello everybody, welcome to Shaders Monthly. Today we talk about procedural textures. In the last two episodes of Shaders Monthly, we introduced 2D texture mapping and MIP maps. The textures were created from raster images and their pixel data. In contrast, procedural textures are created by a mathematical description of the depicted shapes and structures. This has several advantages. Firstly, a mathematical representation requires almost no memory. We don't need to load and store pixel data. Secondly, we don't have to worry about the resolution of the texture. This is demonstrated by the shown example. On the left, you see a pixel-based 2D texture, and on the right, a procedural texture. When we zoom in, the individual pixels become visible on the left. The procedural texture on the right has an almost infinite resolution that is only limited by the floating point precision. No MIP maps and texture filtering are required. The disadvantage of procedural textures is that the mathematical descriptions are evaluated at rendering time. If the complexity of the depicted content is high, the computational effort might become too large for a real-time application. As a practical example, let's implement the procedural texture that is shown on the right in GLSL. I will use the GSN Composer at gsn-lib.org as a shader editor here, but you can use any other shader editor as well. Links to examples that execute the same shader code using C++ or Java can be found in the video description. Our implementation starts with our example from episode number 5, in which we have applied a texture to a triangle. Click Project and type in the project name Shaders Monthly 05 and click Open Existing. Then open the graph texture triangle and press play in the time control panel. Let's replace the triangle with a quad. Click Create and navigate to 3D, Compute, Generate, Plane. Then we connect the Mesh Data node to the Mesh Input slot of the shader node. Perfect, we are rendering a quad that exactly fits the size of the frame buffer. The currently applied texture is this image here. We replace it with a raster image that serves as a reference for our implementation. Let's have a look at the shader code. We select the shader node and click the Edit Code button. This dialog is the shader editor of the GSN Composer. In the top section we can define the vertex shader and in the bottom section the fragment shader. Here we have the uniform variable sampler2D_my_texture that represents the pixel-based input texture. In the fragment shader we use the built-in GLSL texture function to get a color value from the texture. The first parameter is the sampler2D variable and the second parameter is the current texture coordinate. The next line writes the texture color to the frame buffer pixel. We define a variable uniform float scale and use it to scale the position inputs in the vertex shader. We close the shader editor and test the scaling parameter. When we zoom in, we can see the individual pixels and the staircase effect at the border of the shapes, which is called aliasing. We clone the shader node. In this new shader node we are going to implement the procedural texture. To debug the mathematical functions, we crop out a single row from the output image and display it as a graph. Image processing, compute, modify, crop. Width 1024, height 1, offset y 512. Which means we crop out an image row at the center of the image. We convert the image row to a signal. Image processing, compute, convert to signal. And display the signal as a graph. Signal processing, compute, helper, graph plotter. The texture coordinates are in the range from 0 to 1. Therefore, we set the xmax parameter of the graph plotter to 1, xmin to 0. We enable the shift parameter and as a label we put extracted image row. We select the shader node and open the shader editor. The sampler2D uniform variable can be deleted. Instead, I paste several uniform variables that I have prepared beforehand. These are mostly color values that are required for the different components of the procedural texture. Next, we replace texture myTexture with myProceduralTexture. We define the function vec4 myProceduralTexture. The texture coordinates are passed via a vec2 that we call pos. We first simply return the texture coordinates in the red and green channel. Return vec4 pos 0, 1. We see at the shader output that texture coordinates are in the range from 0 to 1 in both dimensions. A texture coordinate of 0, 0 is at the bottom left corner, 1, 0 at the bottom right corner, 0, 1 at the top left corner, and 1, 1 at the top right corner. Now let's start by drawing a circle. This can be achieved by using a signed distance function, or SDF for short. The signed distance function of the circle can be computed as shown on this slide. Given a 2D position P and a circle with center C and radius R, we want to compute the distance from P to the border of the circle. The distance to the border is given by the length of the vector P minus C minus the radius of the circle. Let's plot the signed distance function for all positions along the shown blue line. Outside of the shape, the signed distance function is positive. At the border of the shape, it is exactly 0, and inside the shape, it is negative. To implement the SDF of a circle in GLSL, we type float circle vec2 pos vec2 center float radius, return length of position minus center minus radius. We create a SDF of a circle with center 0.5, 0.5 and radius 0.25. Float circle SDF equal circle pos vec2 0.5, 0.5, 0.25. To output the SDF as a grayscale value, we define a function. vec4 float to gray, float f, return vec4 vec3f 1.0. And put return float to gray circle SDF in the myProceduralTexture function. Perfect, this looks like the function from the slides. Inside of the circle, the SDF is negative and outside it is positive. If we want to create a mask for the shape of the circle, we can define a fill function. Float fill float SDF. If SDF less equal 0.0, return 1.0, else return 0.0. Return float to gray fill circle SDF. Okay, this looks good. We can change the radius here 0.1, 0.2, 0.3. This works well, but our implementation uses an if-else statement. This branching in the code might slow down the parallel execution. Typically, several shader cores in the GPU share the same control logic and can only compute the same instruction at the same time. If some of these shader cores need to follow the if path and others the else path, they cannot run concurrently. The shader cores must wait for each other and we lose performance. A common approach is to replace the if-else statement with a step function. I will demonstrate the step function here. Remember, pos.x goes linear from 0 to 1. Now, here's the step function. Step 0.5 pos.x. The first parameter of the step function defines the threshold, where the step from 0 to 1 is occurring. If the second parameter is below the threshold, the step function returns 0 and otherwise 1. Currently the threshold is 0.5. This is 0.25 and this is the result for 0.75. By the way, GLSL also provides a function called smoothStep that produces a smooth transition from 0 to 1. SmoothStep 0.4, 0.6, pos.x. The first parameter defines the threshold where the transition starts and the second parameter where the transition ends. This function is used a lot in shader programming, but we don't need it today. Another useful built-in GLSL function is called clamp. Clamp pos.x 0.0, 1.0. The second parameter is the minimal possible value for pos.x. For example, let's put 0.3. The third parameter is the maximal possible value for pos.x. For example, let's put 0.7. Consequently, the clamp function constrains the input to stay within a given range. Now, back to the fill function. In our fill function, we replace the if-else statement with the step function. Our threshold is 0.0, so we type return step 0.0 SDF. Well, almost, the result is flipped. But this can be easily fixed by multiplying the SDF by -1. If we reduce the output resolution, we see that we still have aliasing. The reason is explained on this slide. For each pixel of the output image, we decide with the SDF if we are outside or inside of the circle. The result can be either 0 or 1. But if we look at this pixel, it is only around 25% inside the circle and 75% outside, and consequently our fill function should return 0.25. The most accurate way to perform anti-aliasing is to sample the SDF many times at multiple locations within the pixel and average the results. But every additional sample requires additional computation. Fortunately, a fast approximation can be achieved because we know the SDF. The SDF tells us how far our sample is from the border of the shape. If we sample at the center of the pixel and the SDF is 0, half of the pixel is inside the shape and the fill function should return 0.5. At this location, the pixel is completely outside of the shape and the fill function should return 0. At this location, the pixel is inside of the shape and the fill function should return 1. Consequently, this red curve gives us the graph for the anti-aliased fill function that we want to implement. Now, how can we convert the green SDF into the desired red fill function? First of all, we need to realize that the SDF is computed in the space of texture coordinates and the anti-aliased fill function in pixel coordinates. Furthermore, we see here that the slope of the fill function is 1 unit per pixel. Fortunately, WebGL2 supports OpenGL ES 3.0, which provides the GLSL fWidth function. The fWidth function approximates the sum of the absolute derivatives in x and y by taking the difference between the current pixel and the neighboring pixel value for the given argument. If we use the SDF as an argument, it can give us the slope of the SDF in the unit pixels. If we divide the SDF by this value, the resulting yellow function has a slope of 1 unit per pixel. Perfect, now we multiply by -1 to flip the function upside down. Next we need to add 0.5 to move the curve upwards. Now the slope of the yellow function is perfectly aligned. Then we clamp to the range 0.0 to 1.0 and have achieved what we wanted. We implement this fill function in GLSL. Float fill float SDF return clamp 0.5 minus SDF divided by fWidth SDF 0.0, 1.0. We also define a macro anti_aliasing that turns anti-aliasing on and off. If_def anti_aliasing, the new fill function, #else, the old fill function, #endif. Anti-aliasing is off, anti-aliasing is on. Excellent, this looks good. We set the resolution back to 1024 by 1024. Next, we need a stroke function to draw the border of the shape. Return float to gray stroke circle SDF 0.05. Float stroke, float SDF, float stroke width. Let's have a look at the SDF again. Return SDF. We are outside of the shape if the SDS is positive and inside otherwise. We can take the absolute value of the SDF, abs SDF. Now everything would be outside. If we now subtract the stroke width, abs SDF minus stroke width, we see that the area at the border of the shape is inside, which is what we want. If we apply our fill function to this new SDF, we fill only the border of the shape. Fill abs SDF minus stroke width. Excellent, now we can stroke and fill a shape. Next, we implement the SDF of a checkerboard. This will allow us to draw the white grid lines and arrange the circles on the checkerboard grid. Float checkerboard SDF equals checkerboard pos divisions, where divisions is the number of rows and columns of our checkerboard. Return float to gray checkerboard SDF. Float checkerboard vec2 pos float divisions. We start our construction of the checkerboard by drawing stripes in x direction. Return stripes pos.x divisions. Float stripes float x, float divisions, return x. If we want to create an SDF for stripes in the x direction, the SDF must be a triangle wave that oscillates around 0. To this end, we use the built-in GLSL function fract, which returns the fractional part of the argument. Return fract x. Well, this does not change anything at the moment because pos.x is in the range from 0 to 1. But when we multiply x by 2.0, we get two oscillations of a sawtooth wave. The first from 0 to 1 and the second from 1 to 2. The second is mapped to the range of 0 to 1 by the fract function. 3 oscillations, 4 oscillations. The parameter divisions is a uniform variable that is set to 8 at the moment, so we get 8 oscillations of the sawtooth wave. How can we convert the sawtooth wave to a triangle wave? We subtract 0.5 and take the absolute value. And times 2.0 minus 0.5 to center the triangle wave at 0. Now, if we fill this, we see that we get 8 black and 8 white stripes. Instead, we want 8 stripes in total. So we put 0.5 here. The slope of the triangle wave is much too steep. Instead, we need a slope of 1.0. This can be achieved by dividing by the number of divisions. We can use the same function to produce stripes in the y direction by using pos.y as an argument for our stripes function. The nice thing about SDFs is that you can apply set operations. On this slide you see the GLSL functions for union, difference and intersection. However, the difference in intersection operations are not exact for the inside of the shape. We copy these functions into our shader. Fill difference SDF, stripes, pos.x, divisions, stripes pos.y, divisions. This is part 1 of the checkerboard SDF. Then we translate the SDF by one division. Vec2 pos trans equals pos plus 1.0 divided by divisions. Float part 2 equals difference SDF stripes postrans.x divisions, stripes postrans.y divisions. And then take the union of both parts. Return fill union SDF part 1, part 2. Or we stroke the border, stroke with a width of 0.01. Okay, now we have implemented the required functions to put it all together. Vec4 color equals Vec4 0. Return color. We start with the gradient in the background. Vec4 gradient color equals mix gradient color A, gradient color B, pos.x. Color plus equal gradient color. The built-in GLSL function mix performs a linear interpolation between the first and the second argument using the third argument as the interpolation weight. Next, we stroke the checkerboard grid. Float grid mask equals stroke checkerboard SDF 0.05 divided by divisions. Color equals mix color grid mask times color grid.a. We multiply the grid mask with the alpha channel of the grid color here. This way, if the alpha channel of the grid color is less than 1, the RGB values of the grid color are weighted less in the mix. Now we draw the filled circle. Float circle mask equals fill circle SDF, color equals mix color fill color circle mask times fill color.a. We need a circle for every division, so we use the fract function to subdivide the domain. Vec2 div pos equals fract divisions times pos. Float circle SDF equals circles div pos Vec2 0.5, 0.5, 0.3. We need to mask out some of the circles with the checkerboard SDF. Float checker mask equals fill checkerboard SDF. Color equals mix checker mask times circle mask. Okay, it looks like we need to shift the checkerboard by half a division. Float shifted grid SDF equals checkerboard pos plus 0.5 divided by divisions, divisions. Float checker mask equals fill shifted grid SDF. Almost there, only the circle strokes are missing. Float circle stroke mask equals stroke circle SDF 0.05. Color equals mix color stroke color checker mask times circle stroke mask times stroke color.a. Done. Now we connect the scale node to both shader nodes and compare the output of the pixel-based texture and our new procedural texture. As expected, the procedural texture is not affected by the scaling. A nice feature is that we can change the parameters of the procedural texture over time. Input, compute, time %. Enable as decimal. Public parameters compute, float, mask function. 2.0 times pi times x. And connect this with the graph time slot of the shader. Then we put plus 0.08 times sinus graph time here and have an animated texture. Now let's see how our procedural texture looks on a more complex 3D mesh. We copy the code of the texture. Open the project Stone Demon and select the graph Stone Demon Phong. We open the shader editor and copy our texture code before the main function in the fragment shader. We replace the diffuse texture with my procedural texture. Now we can freely change the number of divisions. This can go up to 100 or as many as you like. As expected, we get no aliasing or other artifacts. Okay, that's it for today. If you have questions, use the comments or get in contact with me. See you at the next episode of Shaders Monthly.